So moving on from what we were just doing, right? I showed you a little bit about a patterning exercise using an image sampler. Um, the the next thing that you'll see that is used very, very frequently, and the reason I'm giving you all these is because they're hot topics right now. Dynamic patterning, using manual-based overridden, repeat patterns, using the image sampler to create graphic patterns. And in this case, we're actually going to create an attractor point or magnet reactive pattern. Okay, so we've spent a fair bit of time on patterns because should you pursue this later on in your academic career, I guarantee you will encounter things that at least somewhat relate to this. Okay, so the first step for us here, and this is kind of a multi-step process, it's a little bit iterative, but we're going to build a definition, and then we're going to expand upon that definition by inserting things, changing little bits, adding things to the end and to the beginning. But to start off, what we're going to do is actually create a grid and then modify the grid cells based on their distance from an attractor point. Okay, so if you think about how we cross-referenced lists in the last definition, right? We took one list, which was the percentage or proportion of gray that particular pixel value had, and we cross-referenced it with the datum or location of all the other points. And we used that to define the radius, right? So every radius was slightly different. Making sense how we cross-reference those two lists? Well, we're going to do something very similar now, where we can take a list of rectangles or cells for the grid and map that up to a list of distances to a point, and then have them scale referentially to their cross-reference. Okay? So that's a description of what we're doing. So the first step for us, because we're working with a grid, is to obviously drop in a square grid. So let's go to Vector and Grid. And this one you're already familiar with, so I think I don't have to walk you through everything. What I do want to do is change the size to something that's significant, not too small, not too big. So I'll do 0, starting at like 5 for the size. And I'll just use the same number of sliders from 0 to 10 for the x-axis and the y-axis counts. So I can go up to 10 in either direction. I'll max it out at 10 for this exercise. Okay, and what I'm going to do is actually create a point on every single, or not, sorry, not a point, create a rectangle on every single point of the grid. So that would be under curve and primitive and rectangle. And I'll plug that in to the P for the base plane. And now you can see that I've got this array of rectangles that are on the grid. And something that is relatively significant, I think, is that these x and y values are based off of domains. So rather than overriding the domain with a singular number in this case, because we want it to be centered on the point or the intersection of these cells, we are actually going to use a domain. So we're going to construct a domain. So I'll go to Math, Domain, construct a domain. And because we're using a square grid, my domain will be let's see, I want 0. So A is going to stay at 0. And actually, I don't think it can actually be 0. But Y, well, no, I'll just make individual sliders because I'm not sure exactly how I want to map it yet. So I'm going to say 1 to 10. So domain start at 1, and domain end at 10. And now you'll see that that domain is saying anywhere from 1 to 10. So I'm going to say x. Oh, you know what? I do want this to be a static number. I'm sorry. Let me go back. What I want is for the... Yeah. It's going to have to be the grid size. Oh, sorry. I remember what I wanted to do. So what I wanted to do is actually size this domain to be the size of the grid cell. But it has to be half of the size of the grid cell because it's going negative in one direction and positive in the other. Okay, so their maximum values are going to meet up at a coincident edge line. So that looks like this. The lowest would be the negative half of the grid cell size, so that would be 5. I can plug that in here. And I'm going to make that a negative. So go to operators, go to negative, and then let's drop an expression on that that says x divided by 2, and we'll commit that change. And then the positive for b, which is our end, let me just do it like this here. So the positive one is also going to be x divided by 2. So that when we plug that into x and we plug that into y, we have our rectangles that actually create another grid. Okay, so it creates a grid that's based on the center point of the grid that we originally constructed. But you'll see why it's significant once we get into the scalar part of this. So now to test it, just try sizing your grid up and down, and it should remain looking like an original grid, like that. Okay, so the thing that we're going to do with this is scale each of these rectangles based on their distance from a point. So I'm going to go and jump all the way out to transform and affine and drop in this scale. Group that, that's under transform again, affine. And let's just take a look at what it looks like if I just scale the geometry. Okay, so I've got the R, the rectangle is going to go into the G input for the geometry of scale. And notice how right off the bat, it scales the entire array of rectangles down toward my origin. That's not what I want. What I want is for it to scale each individual rectangle. So I need to, let's see, does it need to be flattened here? No, this should work. That's what I want to do. Okay, yes?
What is your expression in your domain?
X divided by 2. Okay, so this is scaling each individual rectangle by its individual origin point. Okay, does that make sense there? So I didn't flatten them yet. I might have to later, but I didn't flatten them yet. And then ultimately, if I drop a slider in from 0 is less than, well, I'll do like, well, no, I guess, yeah, 0 less than 2.55, less than 5. I have no idea what this is going to give me, but plug it in and play around with it. So as I scale it down, you see that they get smaller and larger in their respective locations around their own center point. Okay, so this is all very familiar. I know that you guys know this. So I can go larger than with this one or less than. If I wanted to max out at full size, I would just make it 2:1. Okay, so what questions do you have about this so far? All right, so in the next step, we're going to introduce an attractor point, which means we're going to scale every single one of these rectangles individually based on a new domain that references its distance from that point.